All right, guys, in this portion of the spreadsheet, we are setting the matrix up. And Keanu Reeves, I need you to save me from the lab data because you need to kind of tell me what goes where and how to do these calculations in order to do them the right way. So this table for part D, this is where we're working right here. There are blue values that are here, and blue values I like to use because these are your laboratory data that you have on a report. So that laboratory data is going to basically be your absorbance values. That's what these are. Look, ABS at chrome, ABS at manganese. So you have ran something probably at 440, 430, somewhere in there. And all four of those solutions were analyzed at that wavelength. And then your manganese was 5 something. So 520, 530, somewhere in that realm. And all four of those were ran at that wavelength. So these are the absorbance values that you obtained from those runs. So for instance, I dialed my UV at 431. I did a fixed run, and that fixed run was bloop, 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 bloop. So the chromium was ran at 431, and I had a really high absorbance value, 0.541, and it should, because that's the flavor that chromium really likes. Your manganese had a really low absorbance. And you know, that makes sense because it's not the best flavor that manganese likes. It doesn't want anything to do with it. So that manganese has a really low absorbance due to that. So 0.051. And then you made a mixed, and this was your mix that you made. And that mixture was 0.561. Keep in mind that absorbance is due to some chromium that absorbs mainly at 431, but also a little smidge of manganese is picking up absorbance and contributing to that number. And you can see that because manganese does have an absorbance at 431. It's really low, but it's there. It's 051 in this case. And then finally an unknown, and the unknown is 0.103. So this was the sample that was provided to you by a lab instructor, and you diluted it to the line with the proper solvent, and you ran it. The same thing happens at 525. That is your fixed wavelength of manganese. And then at 525, you ran bloop, 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 each one of those. Those were the absorbance values. Notice what happens. Chromium hates the flavor of 525. So chromium doesn't really want to absorb, and its absorbance plummets. 0.024 is that one. Manganese loves 525. That's what it's going to get on the menu every single time. So its absorbance skyrockets through the roof, and here it's 0.937. The known mix also absorbs 0.973, but keep in mind this 0.973 is going to be part chromium, part manganese. And then the unknown is what we've made, and we've provided that to you, and you ran it, and the absorbance is 0.294. Next up for part D, down here at the very bottom, you're seeing at chrome and at manganese. These are molar absorptivity values that have been calculated. So the molar absorptivity basically refers to Beers's law, A equals EBC. So to calculate molar absorptivity, we're going to take absorbance divided by the concentration. In order to get the 450, what should have happened here is that you are going to take the absorbance of chromium at 431. And that absorbance is that absorbance is 0.541. And then you're going to divide it by the concentration that you prepped in your work. And that concentration's up here. This is what was used to make them and to run them, right? These were standards. So 0.000405. When you do that, if I pull up the calculator, I'm going to key in 0.541 divided by 0.00405. And I hit equal. What on earth? Well, here's why. This is a very common mistake that people do, you included, if you're not paying attention. So it is absorbance over the concentration. That is correct. It is the absorbance of 0.541 for chromium. And up here in the top, you got to keep in mind, chromium is listed in the second line, not the first. So what this means is that I use the permanganate concentration and not the chromium concentration. So instead of dividing by 0.000405, we're going to divide by 0.001202. So when you do that, I'm going to come in, clear this out. I'm going to take 0.541 divided by 0.001202, and I hit equal. Ta-da! It is 450.08 or 09, and that is the molar absorptivity of chromium at chromium's wavelength. So what will happen is that here in this line, 19.97, you do the same thing. You take the absorbance of manganese, right? That's what this is. Manganese's wavelength. So this is the chromium column, and we want chromium, so that 0.024 divided by the concentration. So I'll bring up the calculator. 0.024 divided by, and this is chromium sample at manganese's wavelength. That's how I read this chart. So the concentration of chromium is still 0.001202. And I get 19.97. So I'll do the same thing for this side of that table. These are the manganese solutions. And it's manganese's absorptivity at chromium's wavelength and manganese molar absorptivity at manganese's wavelength. Again, that's how that chart is ordered. So chromium's molar absorptivity should be higher at chrome because that's the flavor it likes and it eats more of it. Manganese's molar absorptivity should be higher at manganese because that's the flavor of wavelength it likes, and therefore it will eat more of it. So your numbers will be different based on what you made, based on your absorbance values, but that is how you complete that small little table in part D of the spreadsheet. Now we get to the good part. And this good part is part E, solving for the concentration. So, hello, yeah, Keanu Reeves, matrix. This is where this is going to come into play. So a matrix is basically divide, and we've got a matrix on top and a matrix on the bottom, and we're going to have to learn how on earth can we solve for this type of algebraic problem, especially if it's been a little bit since we've seen it. So in order to do this, what's going to happen in the molar absorptivity absorbance realm, you saw a lot of these example of a matrix problems, right? You saw that. We did some lecture videos about it. It was in the playlist. You probably watched it. At least I hope you did. But that gave you some examples on how to set up a matrix and how to solve it the proper way. So this table down here at the bottom is going to be divided up into two halves. This is going to be for our known, and this is going to be for the unknown. And I'm only going to talk about one side because the other side mimics it. There's really no difference in it at all. So we need to kind of figure out what numbers actually go where. Well, if I take a look at the matrix up here on top, concentration for chromium, concentration for manganese. This is the whole point of trying to figure out how much is actually there. So if I look at these values, let's think about where these values are coming from. You know, what are they? What number goes where? Blah, 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 blah. So the proper order of the numbers, if you look at 0.561 and 0.973, these are absorbance values, and they are absorbance values of the known. So hold on, let me kind of get rid of a lot of this scribble, because we don't like scribble. It's making things too ugly, too messy, too many arrows pointed in all kinds of directions. We don't need all of this. We're going to get rid of it. All right. So if we go and take a look at the matrix, the 0.561 and the 0.973, those are the absorbance values of your known, because we're working with the known. And up on top is the absorbance of chrome. And then down below is the absorbance at manganese. So that's kind of the setup there to the left-hand side. On the right-hand side, these are actually molar absorptivities. And these molar absorptivities you calculated from up above. So again, these are just references. I want you to key in equal and click the number. Key in equal, hit the numbers. Don't manually type these in. You'll get a better answer if you reference the entire number, not rounded off. So these molar absorptivities, this is the molar absorptivity at, look, this is the manganese's wavelength. So this is molar absorptivity of manganese, molar absorptivity of the manganese at the two different wavelengths that was ran. So those are just copy down, really all that you need. But hit equal and click 126. Hit equal and then click 2315, and it copies those numbers down there. The bottom issue is just really your molar absorptivity table together as a whole in the way that it's ordered. So again, molar absorptivity of chrome, molar absorptivity at chrome, one at chrome and one at manganese. And then molar absorptivity of manganese, molar absorptivity of manganese, again at the low and the high value. That table looks identical to the table that you presented up here at the top. All right. So now it's a matter of, okay, well, if that is how we saw for chromium, how is manganese any different? It's not that much different. Manganese is the opposite side of that, right? So we still have a top and we still have a bottom. What you're finding here is that instead of the absorbances listed to the left, it's the absorbances of the manganese solutions, and that manganese is what you're trying to solve for. So that's going to show up on the right-hand side here. So that 561 and that 973, hello, it's right there. So we just kind of flipped it. The rest of it is exactly the same. If you take a look at the bottom, these are molar absorptivities of chromes and molar absorptivities of manganeses. These are in the exact same order. There's no difference here between those bottom numbers. It's all exactly the same, but equal, and then click on the value. Equal, click on the value. Don't just type them in. And then finally, this 450 and the 19, where is that coming from? Well, those are the molar absorptivities of chromium up here at the very top. So molar absorptivity of chrome and molar absorptivity of chrome. So in order to find chromium, you are using the absorbances of the chromium solutions in the matrix. In order to find manganese, you are using the absorbances of the manganese solutions in the matrix. And all of the other values are these molar absorptivities that each piece contributes to the total absorbance. I mean, that's why this is set up the way that it is. All right, so in order to solve for a matrix, let's review a little bit of algebra if you have had that class. When you get into a matrix, there's a top portion and there's a bottom portion. So if I go and kind of copy in what was pasted into the spreadsheet, 0.561 and then 0.973 and then 126, I'm just going to round it off to prevent messiness, and then 2315. There's numbers here. What do we do with those numbers? How do we solve for that? Because it looks like this whole garbage that I just wrote down simplifies to 1176.167. How on earth does it do that? Like, what math is behind that calculation? How do we do this type of matrix problem? Well, here's the secret. It's cross multiplication and subtraction. So you're actually going to take 0.561 and 2315 and you multiply these numbers. That's what you do there. And then on the other side, what you'll do is that you will take 0.973 and 126 and you multiply those numbers. And those products get subtracted from each other. All right, so I'm going to erase that bottom. Keep in mind there is a bottom piece. It's solved the same. But what this means, to solve this setup, I'm going to take 0.561 times 2315 and then subtract that from 0.973 times 126. All right, so if I come over, I'm going to type 0.561 multiplied by 2315, and I get 1298,715. And then I do the same on the other side. That's 0.973 times 126, and I get 122.598. And then to solve for the top portion of the matrix, 1298.715 minus 122.598, and that gets me 1176. And that's where that 1176 comes from in the spreadsheet that you see over on the left-hand side of your screen. I do the bottom the same way. So I'm going to click this cell and I'm going to hit equal, and I'll open the parentheses up. And I'm going to say, hey, I need 450 times 2315. Close that parentheses up, subtract, open a parentheses back up, the 19.967 times the 126. Close the parentheses back off and hit enter. And that's where that value comes in as well. That's how you solve for a matrix problem. You take the two corners, multiply them, take the other two corners, multiply those, and then do the difference of. So now to calculate the concentration of the chromium, I am going to take 1176 divided by 103.9487. That is why this is set up that way. That's why there's a line in between those two numbers. Key that in, equal, click 1176 divided by 103.9487, and I get 0.00113. The same thing happens for the concentration of manganese. Again, cross multiply, subtract those, target the bottom, cross multiply, subtract those. You'll end up with the same number as before, same values. 426 divided by 103.9487 is 0.00411. And these values are your calculated values of the known concentrations. So in the part F of the spreadsheet that you see down here at the very bottom, you're going to see for the known mixture 00113 and 000411. These values are coming from here. That is the experimental concentrations that you obtained when you made your solutions, when you ran them, when you plugged them into the matrix. It is telling you that these are the concentrations for chrome and for manganese. Again, they're additive. The absorbances are coming from both. The true concentrations, well, you know what those should have been, because you made those. Right up here at the very top, you made these solutions. You know what those should be. They're right here. You weighed them out. You dissolved them. You diluted them. You diluted them again. You got these concentrations and you were like, you know, based on what I measured, based on what I weighed out, these are the concentrations that's in my mix because I calculated them. I know what they're supposed to be. So for these values that you're seeing here, again, you're going to click these cells and you're going to start off with equal, and then you're going to go up here and you're going to click on hello right there. These are your concentrations that will go in. These are the actual ones that you made. This is what you actually did. So to calculate a percent error, well, you'll take those two numbers and subtract them. Like most error calculations, you take a difference. And then you divide by what it should have been theory-wise. And you multiply by 100. You do the same for manganese. And this person did extremely well. 5% and 1% error. This lab does extremely well. And if your elevated percent errors are there, those are massive point deductions that get lost. So be careful. Next up, for the unknown mixture, you're going to key in your numbers that you obtained experimental after the matrix. In this example, these values are from the unknown. So that's this one and that one. Your true concentrations are just as before. There's no difference there. At least there shouldn't be. So these numbers, well, they're going to be based on the volumes that we used. We have taken your concentration. We know how we've diluted it, but you don't. So on my spreadsheet, I'll do something very similar here, but for these, you're actually going to leave blank. I will fill those in for you because I know what I've used. You don't. You're going to have to keep your fingers crossed, and hopefully your error is not going to be a lot. And then the error here, you're actually going to leave those blank as well. I'm going to be okay with that. So leave these blank. And these will also calculate on my side, not on yours. And we hope that those errors are minimized. But you cannot calculate these two sets of data without the volumes that we have used when we made your unknown. And we're going to keep that a secret for you. So folks, that is the spreadsheet. Hopefully you'll get very small, minimal errors. Hopefully this clears up any questions that you have. And if you do have questions about the spreadsheet, you know how to get a hold of me. Come on now, see me in person, send me an email. I might respond, I might not. Who knows? But you'll get to me in some form or fashion. Good luck.